Hello and welcome to the Stardog Academic Training on Reasoning. I'm Jaroslav Pullman. To let you know a bit more about me, I'm a solutions architect at Stardog and passionate about solving problems with customers. In the past 20 years, I've engineered solutions for various domains spanning from interactive speech applications, text processing, IoT systems, and a plethora of semantic web services. Today, I'm going to walk you through making implicit information explicit through reasoning. In this training session, you will become familiar with modeling standards like RDF schema and OL, learn about the means to unveil implicit information such as Stardog rules, and in conclusion, to understand the benefits of logical reasoning. Reasoning is the process of deriving new facts, called inferences, from an existing data set based on definitions in the data model, called axioms, and a set of applicable rules. The process of reasoning is also known as inference. They are synonyms. At Stardog, we adopted the latter term and talk about inferencing or inference engine, etc. Graph schemas and the more expressive ontologies model a domain in such a way that further conclusions could be drawn from the data using logical inference. This is a set of rules based on proven knowledge representation formalisms such as the description logic, a decidable and efficient subset of the first-order logic. Logical inference makes implicit information explicit, for example by classifying resources based on their attributes or computing new values. Inferences may create views of data to align it across applications or links between previously unconnected nodes. Being based on well-defined rules, the results of logical reasoning could be proven and explained, unlike statistical inference, which models trained on bulk data are a black box. Last but not least, reasoning will verify the correctness of knowledge modeling and unveil potential inconsistencies. As outlined by the canonical semantic web stack diagram, there are layers of standards involved in reasoning. Each of the layers adds expressivity to the modeling and expands conclusions that could be drawn. The core Resource Description Framework, RDF, specifies a triple-based structure to assert facts about resources identified by an IRI. The RDF schema language defines a vocabulary to construct simple RDF models as hierarchies of classes and properties. The web ontology language OL allows, among others, to express the meaning of classes via structural expressions. Finally, the semantic web rule language SPIRL and the related Stardog rules provide means to leverage if-then rules and auxiliary functions in reasoning. The Resource Description Framework RDF specifies triples of subject, predicate, and object as the abstract graph structure. Triples encode statements about graph nodes identified by an internationalized resource identifier IRI. RDF defines the root class of predicates, RDF property, as a distinguished set of identifiers such as RDF type, which links an instance to the corresponding class, and RDF value, acting as the standard value attribute of structured nodes. Extending upon core RDF, the data modeling vocabulary RDF schema allows for definition of classes and properties that are optionally organized into hierarchies. A class comprises a set of instances with some common characteristics. Likewise, data types may be defined for a coherent set of literal values that correspond to a standard XML schema or a custom data type. RDF schema allows to define property hierarchies, where predicate RDF as subproperty of, the class a property applies to, RDF as domain, and the type of values the property links to, RDF as range. The information implied by schema hierarchies allow your queries to be less precise about the type of resources and their relationships. Such you may query for the more general types of resources or relationships, and the inference will also match any derived classes and properties down the hierarchy by traversing the predicates RDFS subclass of and RDFS subproperty of. The same effect of hierarchy inference may be achieved by a sparkle property path, where the RDF type predicate is followed by a sequence of 0 or more repetitions of the RDFS subclass of or RDFS subproperty of predicate respectively. In this example, the class artist comprises a person or group of people creating and performing music. The query for artists will retrieve instances of any of its subclasses. The class solo artist is an intersection of the classes artist and person to distinguish this kind of artist from a band. Thanks to hierarchy inference, the solo artist John Lennon will likewise be identified as a person. Unlike traditional schema languages, RDF schema is intended to draw simple inferences from the data rather than to enforce validity constraints on the data. So the domain and value range classes specified for the track property will accordingly classify the subject and object resources related by this property in a triple. Accordingly, the resource let it be is inferred to be of type album and across the universe of type song. The web ontology language OL is a logic-based language supporting a formal description and automated reasoning about RDF resources. Compared to RDF schema, it differentiates RDF properties that are relations of type OL object property and attributes of type OL data type property. It defines further characteristics of properties such as uniqueness by the dedicated property type OL functional property. OL captures the logical relationships among modeling constructs, such as whether two classes have the same meaning, it is their equivalent, or incompatible, it is disjoint. OL class expressions allow to capture the meaning of a class by expressing constraints on values or cardinality of their instance properties. As stated previously, a class represents a set of instances with some common characteristics. The set of class instances is called class extension. Relationships between classes are expressed in terms of set theory as a partial, complete, or missing overlap of class extensions and defined by the class axioms RDFS subclass of, all equivalent class, and all disjoint with, respectively. The extension of a superclass includes the extensions of its subclasses. In our music domain, the superclass artist, depicted as the orange set, splits up into the subclasses solo artist and band. Equivalent classes share the same extension as they refer to the same set of instances. You may think of equivalent classes as mutually subclassing each other. The concepts song and track may be used interchangeably in our toy domain and thus represent two equivalent classes. Disjoint classes represent incompatible concepts and have no instances in common. Such members of one class may not at the same time be members of the other class. It is a common pattern to express disjointness of sibling subclasses in order to completely partition the extension of the superclass. We may state solo artist and band classes to be disjoint, since a band is expected to comprise more than a single artist. In RDF, properties are IRAs with a global visibility and scope. All class expressions define the class extension, it is set of class instances, based on local property restrictions that specifically apply to instances of that class. A restriction is normally a blank note of type OL restriction that refers to the constraint property via the predicate OL on property. The existential quantification requires instances of the class to have at least one property value of type specified by the OL sum values from predicate. The universal quantification requires all known values of the constraint property to be of type specified by the all values from predicate. Please note the universal quantification does not imply the property to be assigned on class instances at all. Cardinality restrictions, for example all cardinality, constrain the minimum, maximum, or exact number of distinct values a constraint property should take on instances of the class. All profiles have only a limited support for cardinality restrictions. You may need to choose ODL for a full support. The value restrictions require the constraint property to have at least the given value specified by predicate all has value. In the example snippet, a rock album is required to have the genre rock music. Next to expressing classes via property restrictions, you may enumerate the class instances via a list referenced by the predicate all one-off. This instance listing is assumed to be exhaustive. Any instances asserted further will make the database inconsistent. Class axioms introduced earlier may be used to define a name class based on class restrictions. The necessary and sufficient conditions need to hold for individuals in order to be classified as instances of this class. In the first case, the name class C extends from restriction R. It is necessary for instance I to match the restriction, but not sufficient to be classified as instance of the particular class C. In the second case, it is the restriction R that extends from the name class C. It is necessary for instance I to match the restriction and sufficient to be classified as instance of the superclass C. In the third case, the name class C and restrictions R are equivalent. For instance I, it is necessary and sufficient to match the restriction in order to be classified as instance of the equivalent class C. We recommend to use equivalent classes with care as they may lead to unintentional inferences. Please test whether the equivalent classes are interchangeable and retain the same meaning in all contexts. This slide contrasts the class definition via the subclass of and equivalent class axioms. In the former, the class expression extends the name class to state one possible condition for an album to classify it as a rock album when it happens to have a genre of rock music. Alternative conditions may exist to classify an album as a rock album independently of genre. The latter states that the condition of having the genre of rock music is exactly the condition for an album to classify it as rock album. Equivalent classes may be used interchangeably. The genre rock music would be inferred for any instance of the class rock album. Logical class constructors compose complex classes by combining class expressions via logical operators and, or, and not. The intersection or logical conjunction of two classes comprises individuals that are instances of both classes. This is equivalent to being subclass of both classes A and B simultaneously. The union or logical disjunction of two classes comprises instances that belong to at least one of those classes. This is equivalent to a common superclass of A and B. The complement or negation of a class comprises a set of individuals which are not member of that class. This is equivalent to asserting class A be disjoint with class C. This example models the class rock band as a band which has the genre rock set for at least one of its albums. As mentioned in the introduction, all differentiates between attributes that accept literal values and relations that link resources. All axioms either define properties relative to other properties, for example to state that they are equivalent, or they express the nature of a single property, such as being unique. Depending on property type, some axioms apply to both attributes and relations, some only to relations due to nature of the RDF graph. The inverse of axiom, for example, flips the direction of a relationship, making the original range class the domain of the inverse relation. In RDF, only resources may become subjects of a triple, so this axiom applies to object properties only. Equivalent properties are aliases that may be used interchangeably to connect the same sets of individuals. In the example, writer and order represent the same relationship. Consider extending a property via the RDFS subproperty of predicate when it doesn't share all implications of the more specific subproperty, for example, composer. Conversely, disjoint properties must not be used interchangeably and may only connect distinct sets of individuals. As disjointness primarily targets validation, we recommend using shackle constraints, for example, the shackle disjoint constraint to prove. RDF is a directed labeled graph where properties link subjects to objects of statements. Properties are directional. In this example, writer links instances of the class song to instances of the class songwriter. An inverse property flips the direction of the original property. It refers from object to subject of the original property. Please note, the same effect could be achieved via the Sparkle inverse property path. The property chain infers a new direct relation between two nodes that are connected via a path of enumerated intermediary relations. The effective number of hops in the chain may vary, since the intermediary relations themselves may either be asserted or inferred. In the example, the relation co-writer decomposes into a sequence of the writer of and writer predicates, as demonstrated by the equivalent Sparkle sequence property path. As a special case of a property chain, a transitive property relates a resource to any other resources connected by subsequent occurrences of this property. It will infer a new edge between nodes connected by a path of the same property at arbitrary length. In the above example, Paul McCartney is transitively connected to Adele via her connection to Paul Epworth. The same effect could be achieved via the Sparkle property path with a plus operator that matches one or more property iterations. Reflexive properties may relate an individual to itself. It is subject and object may be the same node. They are rarely used, for example, to express containment relations, as anything is trivially part of itself. More common are irreflexive properties that may connect distinct individuals only. It is the same individual cannot be related to itself via an irreflexive property. As with all property disjoint with axiom, we recommend using shackle constraints, for example the shackle disjoint constraint, to test irreflexive properties. Symmetric properties hold in both directions. It is the direction of symmetric properties is irrelevant. In the example, Adele is connected to Paul McCartney and vice versa. A symmetric property is its own inverse. It may be represented as a Sparkle alternative property path of the property and its inverse. Functional properties link a value that is unique for a particular resource, for example the publication date of an album. There is at most one outgoing property occurrence. It is at most one referred triple object. We recommend to validate functional properties via the shackle max count constraint. An inverse functional property links to a globally unique value, for example an ISBN number. It is at most one incoming property occurrence. It is at most one referring triple subject. Inverse functional properties may be validated by a combination of shackle max count and inverse path constraints. This example leverages all axioms and inference rules to detect an inconsistency in the dataset. The range of the property ISBN 13 is an International Standard Book Number ISBN resource. This media identifier is stated to uniquely identify a resource because the property is of type all inverse functional property. Two resources with the same ISBN 13 value could be inferred to be equivalent. Due to non-unique naming assumption in all, different IRIs do not necessarily refer to distinct resources, so we'll need to explicitly state that the album Abbey Road is different from the other album. Using the expressive description logic reasoning mode, Stardog will detect an inconsistency by executing the reasoning explain command, since two distinct resources may not share the same unique identifier. These two examples explore alternative ways of validating inverse functional properties. The Sparkle query above counts albums grouped by ISBN, indicating any duplicate use of the identifier. The shackle shape below targets at the ISBN resources, constraining the number of the incoming ISBN 13 properties to at most one. Because of the inverse property path, the ISBN identifier has to be a resource and not a literal. Similar to an inverse functional property, a key expresses a globally unique identifier for class instances. A class may list data and object properties via the OL has key predicate, which values will jointly constitute a key for an instance of this class. A number of RDFS and OL axioms was initially designed for validation. It is consistency checking of datasets with regard to a model. The Shapes Constraint Language shackle is a W3C standard dedicated to graph validation, which is capable of implementing most of these axioms. Given its popularity, built-in support for automated testing and report generation, we recommend to implement axioms such as RDFS domain, RDFS range, all functional or inverse functional properties via shackle constraints. Please have a look at the Stardog academic training on data quality for details. And even for some reasoning axioms, alternatives exist based on plain Sparkle property path. Consider this option for simpler focused use cases which do not require a full-fledged inference. So far we considered all class and property axioms. The all sameAs predicate operates on individuals, it is class instances. It declares that different resources represent the same entity. The alias resources will be merged automatically at logical level, making use of the all sameAs characteristics. It is being reflexive, symmetric, and transitive. The example states that the identifier Ringo Starr in the default namespace represents the same resource as the IRIs Ringo Starr and Richard Starkey in the DBpedia namespace, so they may be used interchangeably. In Stardog, one canonical individual is selected from a set of equivalent resources, aliases. This representative handle is chosen randomly, but remains fixed until the set has changed via an update to the schema or data. Only this canonical individual is returned by queries that match any of the aliases, regardless of their number. Nevertheless, you may use any of the asserted or inferred aliases in your queries, not only the canonical one. Unlike other inferences that are derived at query time, all sameAs inferences are computed eagerly and materialized at data ingestion. The all sameAs index is updated automatically whenever the database changed. The extent of inferences depends on the reasoning type configured where the database property reasoning.sameAs. For the value of, no inferences are drawn. Queries will retrieve only the asserted all sameAs triples. The reasoning type on will extend the asserted statements thanks to the reflexivity, symmetry, and transitivity of the all sameAs predicate. The full mode will further leverage the functional, inverse functional, and has key axioms to infer equivalence of individuals. In the first example, the resources Ringo Starr and Richard Starkey are inferred to be the same thanks to the transitivity and symmetry of the asserted all sameAs relationship. In the second example, the resources Abbey Road and My Album are inferred to be equivalent because they share the same global unique ISBN identifier. In the last example, a composite key is defined by the class Album, assuming the combination of the release date and producer will uniquely identify its instances. The albums Abbey Road and My Other Album are inferred to be equivalent since sharing the same key. Next to RDFS and all axioms, inferences may be drawn based on simple if-then rules. The condition, if part, and consequence, then part, consist of basic graph patterns optionally augmented by filter and bind clauses. At query time, when the condition is true, the graph pattern in the consequence will generate inferred variable bindings. The example Stardog rule classifies a band depending on the genre of its album as a rock band, similar to the all has value class expression. This syntax extends the turtle notation and may be uploaded to any schema graph via the CLI data add command. Rules may build upon each other, introducing layers of abstraction on top of a dataset. The inferences of the rule 1 and rule 2 in the example are consumed by rule 3, along with facts asserted in the graph. Care should be taken that no cycles occur within a network of interdependent rules. Thanks to the inferred data structure, rules may help to keep up a stable data contract so graph patterns of queries will not break even when the underlying data changed. Rules hide complexity of the raw graph data and details of the evaluation logic. The example rule demonstrates the main capabilities. It classifies track instances based on the length attribute and computes a new inferred property length in hours. Reasoning depends on schema information. It is axioms and rules present in the database. These are just RDF triples loaded like any graph data, for example via the data add command. Stardog will search for this information in schema graphs identified by the database property reasoning.schema.graphs. This configuration comprises the so-called default schema. Stardog further supports reasoning with multiple custom schemas. The term schema refers in this context to a named custom collection of named graphs selected at query time that contain the reasoning axioms. This schema multi-tenancy feature has various benefits. It allows to maintain compatibility with legacy applications, as various versions of a schema may be selected at query time depending on the client. It supports evolution of business rules, for example to encode threshold values for rule-based computation. And, last but not least, partitioning of a large number of axioms and rules into identifiable modules has obvious benefits for scalability and modularization of large models. The individual reasoning schemas are defined by the configuration option reasoning.schemas as a comma-separated collection of schema name graph IRI pairs or via the CLI command reasoning schema. The music schema in this example consists of the name graphs, charts, and albums of the music database. In Stardog, reasoning is disabled by default and is to be explicitly enabled for a query via the reasoning or schema parameters. Stardog allows for debugging of inference results via the reasoning explain command. This returns a minimum set of asserted and inferred statements that is sufficient to logically justify the inference. The explanations of an inference or an inconsistency are organized in a hierarchical structure called proof tree. Nodes representing assertions that lead to an inference are grouped under the inferred node. Related explanations are merged into a single proof tree, the so-called merge proof tree. Alternatives for an explanation are given a numerical ID referring to the respective inference. In Stardog, reasoning is performed at query execution time via the query rewriting technique. Client queries are transparently augmented with respect to the underlying reasoning schema and profile. As mentioned previously, reasoning schemas in Stardog are named sets of custom modeling statements that build up a domain model or parts of it. The reasoning profiles are well-designed assemblies of general modeling constructs and related inference rules. For example, the RDFS profile covers the expressivity of the RDF schema language. The reasoning profile governs which of the schema-supplied axioms are supported and how the original query will be expanded to derive the correct inferences. The expanded query is then executed against the dataset in a standard manner. This approach scales well even for large datasets, as the reasoning is tailored to the actual query. In contrast, the inference materialization technique expands up from the entire dataset with respect to a schema and profile. The inferences are persisted independently of the actual queries. Since this approach operates upon an expanded dataset, there is no overhead at query time, potentially resulting in faster response times. But it is prone to a number of issues. The inference management is rather complex and has to keep up with changes to schema or reasoning profile. The materialization may be computationally expensive and consume significant resources prior to being queried, and the significant increase of data size may introduce a penalty on input-output operations for every query. The old sameAs reasoning is an exception to the default approach. It eagerly materializes inferences on identical individuals to serve the query rewriting process. When there is an emphasis on query performance, consider ingesting the inference results into the database via a Sparkle update query. This materialization will decouple an initial production of inferences in a batch mode from querying when no reasoning is involved. Let's have a look at some examples of inferencing in Stardog. The first demo section demonstrates RDF schema reasoning. For this and the following sections, we have adopted a general pattern and load only data and schema axioms which are required for the respective part. The Sparkle update clauses below will clear the default graph and ingest the specified statements to prevent the demo sections to interfere. The RDF schema defines the top-level class artist, with subclasses band and solo artist. The class solo artist extends from the classes artist and person at the same time and represents their implicit intersection, the concept of a person being an artist. There are only few statements in a demo database stating the Beatles is a band with John Lennon as its member. Thanks to reasoning, we don't need to specify the exact instance type and may query the database in a more fuzzy manner, asking for any kind of artist by referring to the common superclass. Stardog Studio will allow to keep multiple queries or updates in a single tab. It will execute by default one with a focus, so the edit queries next to the data to ease the explanation. Both resources, the Beatles and John Lennon, match the classed artist thanks to transitively resolving the class hierarchy and property definitions. The class and property hierarchies could be traversed without reasoning via this Sparkle property path. Based on its range definition, the values of the property member are inferred to be of type solo artist. This class is further known to be a subclass of person, so we may ask the tiny database about any person it knows, which is John Lennon. The following example of all reasoning demonstrates so-called existential quantification and requires at least one value of given type to exist for the restricted properties. The class album is defined as an intersection of these class descriptions, so individuals with the properties track, producer, and date will be classified as instances of an album. Apparently, the dataset is not sufficient to draw the expected inferences. In order to meet the sum values from restriction, the required types of property values either need to be asserted or inferred, for example, via the property range definition. And this is an example of a class definition combining the sum values from and has value property restrictions. The class rock band is defined as a band with at least one album which genre is rock. Based on the asserted genre of its album Let It Be, the band The Beatles is inferred to be of type rock band. Let's focus on the genre example to showcase the various axioms for defining classes via property restrictions. It further demonstrates how inference could be used both ways, to classify an individual depending on its property value, or to infer the property value based on the instance type. The above subclass of axiom specifies the necessary condition for a rock album, but it's not sufficient to classify Let It Be accordingly. You may use the all-equivalent class axiom to state that a rock album is exactly the same as an album with the genre rock. Or make the property restriction a subclass of the name class. This way, instances of the named superclass are implicitly members of the restriction subclass, so the sufficient and necessary conditions for a classification hold. When it comes to inferring the value of a restricted property based on instance type, you may leverage the original RDFS subclass of axiom and let the name class extend the has-value restriction. Likewise, the all-equivalent class axiom supports inferring the genre of the rock album Let It Be. Looking at the all property axioms, this is an example of a transitive property connecting resources along its path. The same effect could be achieved by the following sparkle property path. The inverse properties are a convenient way of exploring the graph in the opposite direction. Compared to the asserted statement, you may query the graph with the original object Paul McCartney in the subject position. The same effect could be achieved via the inverse sparkle property path or by twisting the order of query variables in the surrounding graph pattern. A number of all property axioms was intended for validation purposes, such as all functional and inverse functional properties. The former expresses a uniqueness constraint local per resource, for example that an album at most have one release date. The functional property constraint was violated for the album Let It Be, as indicated by the CLI command reasoning explain. The inverse functional axiom expresses a global constraint of a single globally unique value, for example the International Standard Book Number, uniquely identifying a published book or a compact disc. The resources Abbey Road and Other Album share the same identifier and are stated to be different to introduce an inconsistency. We do not see the expected warning despite the obvious contradiction. The inference and consistency checking of a dataset is based on the selected reasoning profile. An OL profile is a subset of the OL ontology language that trades expressivity for efficiency of reasoning by restricting the set of axioms a profile supports. This could be configured per database via the reasoning.type property. SL stands for Stardog level and is the recommended setting for most of the reasoning tasks, but in order to determine the inconsistent use of an inverse functional property, we need to choose the expressive ODL profile. The check based on the ODL profile revealed the expected inconsistency. Let's reload the problematic dataset again for sake of a shackle validation. Compared to the concise OL axioms, validation instruction in shackle are encoded via so-called shapes. The node shape album data shape applies to instances of the target class album and generates a warning whenever the maximum count of publishing dates exceeds 1 as specified by the enclosed property shape. The node shape ISBN shape approximates the inverse functional property axiom. It applies to objects of the ISBN 13 property, which are identifier resources, and generates a violation result when there are more than one incoming ISBN 13 links as expressed by the inverse path constraint. The Stardog ICV report command will generate a shackle validation report, a standardized RDF graph structure with a series of validation results of different severity that were generated by matching shapes. The multi-publishing dates are reported for album Let It Be, along with the inconsistent use of the ISBN 13 identifier. The OL sameAs reasoning needs to be enabled first via the reasoning.sameAs property. The setting on will expand asserted sameAs statements and infer the resource Ringo Starr in the default namespace with the same as the resources Ringo Starr and Richard Starkey in the DBpedia namespace. We may query all of these resources interchangeably. With the configuration setting full, sameness of resources will be inferred based on the key, functional, and inverse functional axioms. The albums Abbey Road and Other Album will infer to be the same based on a shared identifier. Finally, let's look at Stardog rules to encode business logic, for example to compute an inferred property value or classified individuals based on their properties. The if clause of the following rule matches album instances with a track of more than 1 hour length. It then converts the length from seconds to hours, exposes this inferred value and the type long track in the then clause. Stardog supports uploading rules as a standalone turtle files or via the embedded syntax as part of a Sparkle update. Stardog allows to reason with multiple schemas and to select at query time the named graphs containing schema information via the associated schema name. Reasoning schemas are configured via the database property reasoning.schemas. The reasoning schema hours contains the previously introduced rule. The schema mins refines the rule and matches albums by tracks of 10 minutes length. This rule does not compute the property length in hours to contrast the use of alternative rules via the associated schema. This stored query optional matches and counts the occurrences of the property length in hours to differentiate the inference results of rules in respective schema. Queries with the reasoning flag leverage the default schema, which commonly comprises schema information in the default and any name graph. "82 long tracks were identified along with 3 matches generated by the rule in the schema hours. The individual reasoning schema might be selected by the schema parameter. That concludes the demo on reasoning. Please find here some recommended resources on the reasoning topic. That concludes the Stardog academic training on reasoning, where we reviewed how to become familiar with modeling standards, learn about the means to unveil implicit information, and to understand the benefits of logical reasoning. Thanks for following along. If you have any questions, please review our frequently asked questions page or head to docs.stardog.com for additional information.